Okay, thank you all for coming to the online class. Sorry, I cannot attend the class on site. So today we will learn another technique in solving recursion equation, actually. So it is still about mathematical analysis of recursive algorithm. But before we start, as usual, we will discuss the previous assignment first. So last week you learned about solving recurrence relation by using homogeneous characteristic equation, right? Characteristic equation for homogeneous linear equation. So homogeneous linear equation basically is an equation, recursive equation, where it has a form of, so we have some like Tn and then plus Tn minus 1 plus Tn minus 2 and so on until Tn minus k, and it must be equal to 0, and it may have some constants here as well, and so on. So, and from this kind of equation, we can have a characteristic equation, and we can solve the equation to find the kind of non-recursive form of the relation we have. So for example, here we have Tn is equal to T3 Tn minus 1 plus 18 Tn minus 2, right? So for homogeneous linear equation, we need to make the right-hand side or one of the side become 0. Okay, we need to make one of the side become 0. So we need to subtract both sides with 3Tn minus 1 and 18Tn minus 2. So we will have Tn minus 3Tn minus 1 minus 18Tn minus 2. It must be equal to 0. And using characteristic equation, we can have r square minus 3r minus 18 equals 0. Then we need to solve this characteristic equation. We can use any method you like. So for example, here we have two numbers that is if we multiply them, it will become minus 18. And if we add them, it will become minus 3. So it will be minus 3, 6, and also plus 3, right? So the solution we have is 6 and also minus 3. So from this solution, we can have a non-recursive form of Tn, which is C1 times R1n plus C2 times R2n. So it will become C1 6n plus C2 times minus 3n. This is called general solution, but it's not yet what we need, because here we have base case. So we will insert the value of T0 and also T1. So from here, 30, we will have something like this. And T0 from the information we have is equal to 0. It must be C1 plus C2. And T1 is C1 plus C2, like this. And from the information we have here, it is equals to 1. It will become 6 C1 minus 3 C2. And using elimination and substitution or any method you like, we can have this is equal to 0 and 6 C1 minus 3c2 is equal to 1. And we can multiply this by 1 and the above with 3, for example. So we have 3c1 plus 3c2 equals to 0. And then this, and if we add them, we will have 9c1 equals to 1. So c1 is equal to 1 over 9. And it means c2 is equal to this, because we can use this equation to find what C2 is. So the final result we have is 1 over 9, 6n minus 1 over 9 minus 3n. And it is in big theta 6 to n. This all. Any question for the problem? Fine, yeah. Okay, next, we will start to learn about another technique. It is the same, basically same technique, which is characteristic equation, but now we will learn about the non-homogeneous part. So the difference is this part is just the same as the previous week, but in the previous week, the right-hand side we have is 0. That is called homogeneous linear recurrence relation. But now, if the other part, the other side is not 0, then it is called non-homogeneous linear recurrence relation. K is just like what we have last week, and Fn must be a non-zero function. And Fn should be able to be expressed as this, where b can be any constant. So it's b to n. And then we have some polynomials. And we have a theorem for a non-homogeneous recurrence relation. We can have a characteristic equation like this. So the difference with what we had before is previously here we can have a characteristic equation like this, right? If it is homogeneous. If it is non-homogeneous, then the right-hand side should be able to be written like this. So it is something to the n, and then times some polynomials. And the power we have here, it will become r minus b. And then the degree of the polynomial means the highest degree we have in the polynomial will become d. Okay, so we will have a new factor for r, which is this. So for example, if we have this as the polynomial, then the degree we have is 2, because the highest rank we have is 2. That is the degree we will have for this. Okay, and if we have this as the polynomial, then the degree is 1, because the highest rank we have is 1. And if we have 8 as the polynomial, then the degree is 0, because it is basically just 8 times n to 0, right? So the degree is 0. So for example, if we have this equation, then we will have k, the largest subtraction for the index is 1. B is 4. What is what number we have, what power number we have, we have 4. And the degree, the polynomial is 1. So the degree is 0, because we have d is the degree of the polynomial. Because this can be written as 4n times 1 So this is the B to N part. 1 is the polynomial part. Another example, this. So this is the left-hand side part. This is Bn, and this is the polynomial. So the highest subtraction we have in the index is 2. The power we have, B, is 4. And the polynomial we have is 8n plus 7. So the degree of the polynomial is 1. Another example, here we have, this is the left-hand side part. This is the right-hand side part. And because we cannot see something power n, of course we know that 1 to n is equal to 1, right? So this is actually can be written as 1 to n, 5n plus 7. That's why we have 1 as b, and the polynomial is 5n plus 7. And the highest subtraction in the index is 1. So we have the degree of the polynomial is 1. Okay, if you have any question, please feel free to raise your hand or just interrupt me, okay? So for example, here we have a reconciliation and we want to solve it so we can know which asymptotic notation it belongs to. So in this case, we know that K, the highest subtraction in the index is 1, and then B is 4 because we have here, and then the polynomial is 2n plus 1, so we have the degree is 1. So the characteristic equation should be r minus 3. It is from the left-hand side, just like what we did for the homogeneous relation. And then for the right-hand side, we will have extra factor here, which is r minus b to d plus 1 equals 0. So it is basically r minus 3, r minus 4 over 2 equals to 0. So we have R1 is 3, R2 is 4, and R3 is 4 as well. Okay, because we have power 2 here, quadratic function. So we have two solution for R. And this means Tn will be C1 times 3 to n plus C2 times 4 to n. And remember, we discussed it last week. If we have double factors like this, we will need to multiply it by n. Okay, so we have C3n times 4n. So now we already have T0. T0 is C1 plus C2 plus 0, right? Because n is equal to 0. And it must be equal to 0. And then we have T1, which is 3C1 plus 4C2 plus 4C3. And it must be equal to 12. Okay, be careful here. We have 3 values to get, but to find the 3 values, the 3 solutions, we will always need at least 3 equations. But because we only have 2 right now, we need another one, right? We need another one, which is T2, and we can get it from here. If we substitute 2 to n, then we will have 3C1 plus 16C2 plus uh, it is 2 times 16, which is 32, 32C3. And we still don't know what it is yet based on the information we currently have. So we need to find it. How do we find it? We can just find it from the formula we have in the first problem. So in the first problem, we know that if n equals to 2, we will have T2 minus 3, 1. So we get it from here, equals 4 squared, 2 times 2 plus 1, right? So it means we know what T1 is, which is 12. So T2 minus 3 times 12 equals 16 times 5. So T2 is 16 times 5 is 80. And then we add this with 36. So T2 is 116. So that's why we can have 116 here. Okay, so we check first how many constants we need to find the value. And if there is 3, then we will need to have 3 equations for the elimination and subtraction. Okay, then from this, you can solve with whatever method you like. You can use elimination and substitution. You can use elementary basic operation, OBE, and any method you like. So for example, here, we just use usual elimination and substitution. And we will get that C1 is 20, C2 is minus 20, and C3 is 8 from the substitution and elimination. And from that, we can just substitute the value to the general solution we have. Okay, is there any question for this? Yes, Rafi, do you have any question?
Permission to ask, Miss.
Yeah.
For the k equals to 1 and b equals to 4, how can we get it, Miss? Sorry.
Okay, what? K equals to 1?
And b equals to 4. How can
Oh,
we know
okay.
it? Sorry.
This one, yeah. So K is the highest subtraction we have in the index. So because it is n minus 0 and minus 1, so the highest subtraction is 1. Okay. Then for B is what we have on the right-hand side, that is to the n. So if this is 3 to n, then B will be 3. If it is nothing, then B will be 1. If it is 7, for example, then B is 7. Okay, just find something to the n. So that is B. The polynomial is like whatever we have next to it. And that's how we can get the degree of the polynomial. Is it clear enough?
Already clear enough, Miss. Thank you.
No worries. Any other question?
Miss, I would like to ask,
Yep.
uh, I didn't really understand about how you get r minus 4 and then to the power of 1 plus 1. How do you, like, how do we determine r minus 4 that you write, you have written here?
This one?
Yes, that one.
Okay. Okay, so basically, for r minus 3, it is just the same as previous week, okay? It is like homogeneous part. It depends on the left-hand side. But for the R minus 4, based on the theorem we have here, this is the R minus 4 part. So other than the homogeneous part we will add this factor, which is R minus B to D plus 1. And back to the example, this is R. Wait. This is R minus B, D plus 1. That's why we have R minus 4, 1 plus 1. Does it make sense?
Yes, miss. Thank you.
No worries. Any other example? Any other question? Okay. So this is another example for it. So for example, for the first one, it means we will have Tn minus 5 Tn minus 1 plus 6 Tn minus 2 equals 5 to n, right? And it means the character, well, B is 5. The polynomial is 1, so the degree is 0. So the characteristic equation will be r squared minus 5 r plus 6. But we need another factor, which is r minus b to d plus 1, which is 1. So we will have r minus 2, r minus 3, r minus 5 equals to 0. So r1 is equal to 2, r2 is equal to 3, and r3 is equal to 5. The rest is like what we had before. But again, since we will have 3 constants, then we will need to find first what T2 is by substitute it n equals to 2 to the relation. Okay. This is also the same for number 2. It means we have b equals to 1 and polynomial is n minus 1. So the degree is 1. So the equation we have is r minus 1, r minus b times d plus 1 equals to 0. So r1, r2, r3 will be equals to 0. And again, Tn will be C1, sorry, not 0, but 1 ya. 1n plus C2n, 1n plus C3n square, 1n, like this. And for the third example, we will have b equals to 2. The polynomial is n, so the degree is 1. So we will have r minus 2 from the left-hand side part, and then r minus b to d plus 1 equals to 2. So we will have r1, r2, and r3 equals to 2. So Tn will be C1 to n, C2n to n plus C3 n square to n. And you will do the rest to find C1, C2, and C3. Any question? Hmm.
Sorry, Miss, can
Maaf ya.
I take a look to the previous slide because I want to take a screenshot, Miss?
This one?
Yes, Miss. Sorry.
Okay.
Okay, thank you, Miss.
No worries. Okay. Clear enough ya? No other question? So for today, you will have assignments still. It is already on LMS. It will be individual because it is similar to last week's problem. Just we have a non-homogeneous part, so it should not be that difficult. You can just submit it through LMS by Sunday night. Okay. And if you have any question for the assignment, you can just chat me on Telegram. Okay, if you have no question, we will do the attendance first. I will stop the recording as well.